Okay, we're gonna start worksheet number 7. It's about arguments. So far in the previous worksheet, we studied statements and how we can put statements together to make conditional statement. In this worksheet, we're gonna start putting statements together and analyze how well these statements are arranged and connected. So it's kind of extension of what we did previously. All right, so logical argument. So this is the title of our worksheet. Argument is a claim that a set of premises support a conclusion. So this is going to be very typical structure of an argument. There's a premise part and there's going to be a conclusion part. A premise is a statement that we assume to be true. So that's the first part of the argument. And the premises and the conclusion are well connected. We say the argument is valid. So when it comes to argument, we talk about the validity of the argument. Before we talk about like if the statement was true or statement was false, now we're going to talk about if argument is valid or argument is invalid. All right. There are two types of argument. First is inductive argument. Inductive argument uses a collection of examples as its premises and uses them to propose a general rule as a conclusion. In other words, it uses specific examples to come up with a general rule. So that's one way of thinking about argument. A bunch of examples, and from there we're going to come up with a general rule. Second type is called a deductive argument. Uses a collection of general rules as its premises and use them to propose a specific example. As a conclusion. In other words, it uses general rules to come up with a specific example. All right. In our class, we're going to do mostly deductive reasoning. Let's look at the next questions here. For each determine the type of argument. The statement that follows, therefore, is the conclusion. Remember we talked about premise part and the conclusion part. So how do I know something is conclusion part? Usually it's the last sentence, or sometimes you'll say, therefore, something. So, all right, let's look at part A. I forgot to bring homework 2 Tuesdays ago. Oops. I forgot to bring homework last Tuesday. Ooh, what's happening here? Therefore, so these are specific examples. 2 Tuesdays ago, I forgot my homework. Last week, I forgot my homework. Therefore, I always forget to bring homework on Tuesdays. So here I noticed that we're starting from examples, and then we're creating general rule. So general rule is I always forget to bring my homework on Tuesday. So this will be inductive reasoning, right? Second, all hipsters like to drink cold brew coffee. I kind of do too, not really, maybe. Casey is a hipster, therefore Casey likes to drink cold brew coffee. All right, so first statement is a general statement. It says all hipsters. It's a general rule. And then Casey is an example of a hipster, so it's giving a specific example. So here they're using deductive reasoning, right? All right, I'm going to have you pause and think about part C and part D. All right, so let's look at number 4. This kind of refers to number 3. From the previous questions, there are 2 arguments that are faulty. Which ones are those, and what do you have to do to show that it's a faulty argument? So let's look at part A here. What if I remembered to bring it this week? I forgot 2 weeks ago, I forgot last week, but what if I don't forget it this week? That's possible. So if that happens, this rule it says I always forget to bring, but it's false if I bring it next week or this week. So part A is a faulty argument because what if I bring it this week? I remember this week's homework. And then this rule is false, right? So this is going to be the case with inductive reasoning. I can come up with the case where the rule is false, right? Just because I forgot last 2 weeks doesn't mean I'm going to forget this week, right? That's why inductive reasoning is not necessarily the best reasoning. All right, let's look at the next. It says, generally speaking, the inductive reasoning can suggest the conclusion is true. It's never be able to logically prove the conclusion, right? All right, let's look at the next part here. An argument consists of two parts, as I said before. The first part is called premise, and the second part is the last part is called conclusion, right? Just kind of review what we just talked about. Usually you have a bunch of premise statements and one conclusion statement. So usually we'll just have one conclusion statement, one. Highlight that. The conclusion statement comes after the phrase therefore, which is symbolically represented by those three dots. So sometimes you see this dot, dot, dot. This means therefore, therefore. That means whatever is following after this is the conclusion. So what's a good argument and what's a bad argument? Here, instead of saying good and bad, we're going to say it's a valid argument. So here I'm going to circle this. An argument is valid if when all the premises are true, the conclusion must be also true. So if the statements are connected, said that all the premises are true, then conclusion has to be true, then the argument is valid. On the other hand, an argument is invalid if there is a case where all the premises are true, but the conclusion is false. Such case is called a counter example. So for the rest of the worksheet, we're going to come up with different strategies to figure out if the argument is valid or invalid. So instead of, again, saying is a good argument or is a bad argument, we're going to say is a valid argument versus is an invalid argument. So for us, we're going to have 4 different ways to analyze the validity of argument. We're going to look at it graphically by using this called Euler diagram. It's basically the same thing as a Venn diagram. We're going to look at the truth table. You're going to recognize the common forms of argument, which is in the next worksheet, and then we're going to use common sense, which is going to be also in the next worksheet. All right, let's look at the graphically analyzing the argument by using Euler diagram. So first, there are 3 types of statements that we can draw. So first statement has a universal quantifier. Again, universal quantifier means like all something is something, right? So all x's are y. So if I were to draw a graph of it, it'd be like this. I'm going to draw x here and then y. So the way a graph is like whatever is inside the x and whatever is. So if you're x, you're inside this circle, that means you're basically inside the y circle as well. So when the statement says all x's are y, the way I'm going to graphically represent it is draw x as inside circle and y as outside the circle. This also corresponds to the statement if x then y. That means if you're x, then you're automatically y, right? That means if you're inside x, you're automatically inside y. So for example, all Angelinos are Californians, right? If you live in LA, basically you live in California. So if I were to draw it, Angelino, if I have 2 circles, which circle should I be? Is LA the circle inside or LA circle outside? Well, obviously LA is inside of California. So this is how I'm going to do it. LA inside, California outside. So all LA are California. So all Angelinos are California, right? So LA is inside, California is outside. If I were to look at it as if-then statement, it's another statement I can make. If you are Angelino, then you're California, right? You are California. So that means Angelino, LA, then you're California, right? If-then statement. So again, LA is inside, California is outside. Okay, so that's the universal quantifier when it says all something are something. All right, let's look at the next one. Existential qualifier, it says some x's are y. So then I can say this is how it's going to. So one isn't necessarily inside the other one. So maybe they have an overlap part. Possibly it's going to be this is X and this is Y, right? What if somebody says some Angelinos are immigrants? If I were to draw it symbolically, it'd be like this is Angelino, LA, immigrants, right? So LA is like my X, immigrants are like my Y. So some people are here like me. I'm an Angelino, I'm an immigrant too. So, and some people are here, Angelinos but not immigrants, and immigrants but not Angelinos, so on and so forth. So this is another case that we can have. And then third case is it says no x's are y. So it's also a universal quantifier. No x's are y, that means it's like this. X here, then y. So for example, I can say no millennials are boomers. Well, so in this case, the millennials, the boomers. I mean, you cannot be millennial and a boomer at the same time, right? So again, notice that like no circle is inside the other circle. They don't even have an overlap. They're completely separated. This is when you have no x's are y. So we have case where they don't intersect at all. That means no x are y. They have intersection, possibly some x's are y. One is completely inside other when it says all x's are y, right? So we have these three cases, possibly. All right, so how do we evaluate the validity of our argument? By using Euler diagram. So first, we draw Euler diagram based on the premises of the argument. And second, we'll look for if there is a way to draw a diagram that makes a conclusion false, then the argument is invalid. Because that's the definition of invalid argument, is when all the premises are true, but the conclusion is false. So if I come up with something like that, then the argument is false. When that happens, we call that a counter example. If the diagram cannot be drawn to make a conclusion false, then the argument is valid. Because that's the definition of valid argument. That means conclusion has to be also true. All right, let's look at some examples here. Number 7. Okay, draw a diagram to determine the validity of each argument. If argument is invalid, describe a counterexample. So this is important. When I show argument is invalid, I have to show where I have a counterexample. So I have to show that this is where the conclusion is false. All right, so let's look at the first. Here, I noticed that I see two statements here, and then I see these 3 dots. So this must be conclusion, right? So 1, 2 are premises. And then number 3 is the conclusion. All right, so it says all cats are something. Oh, so it's universal quantifier. Cats, they're X. All cats are something scared of vacuum cleaner, so that's my Y. So when I do this, it's going to be like this. If you're this. So X is my cats. And scared of vacuum cleaner. So I'm just going to like vacuum. To use. Weird. So if you're a cat, you're inside the cat, obviously. That means you're inside the things that are scared of vacuum cleaners. Okay, fine. Max is a cat. So Max is here. It has to be here. Max. Okay, what's my conclusion? Max is scared of vacuum cleaner. Okay. So Max is, because Max is inside of cat, Max is inside of vacuum cleaner. In order for me to come up with a counterexample, I have to create a case where it's not the case. Is there a case that Max is not scared of vacuum cleaner? That means Max has to be here. But is that possible? No, because it says all cats are scared of. So Max has to be inside the cat because Max is cat by premise number 2. So this is not possible. This is not possible. Only possible for Max to be is inside the cat. That means it has to be inside the vacuum cleaner. So this argument is valid because Max cannot be here. Max can't be here. That would have been my counterexample because Max is outside a vacuum, but that's not possible. Okay, let's look at the second case here. Again, it says all firefighters know CPR. So firefighters is going to be my X, CPR is Y. So if I, because it's all something or something. So if I have to draw a graph of it, that's my firefighter. And then there's like people who know CPR. Right. Again, if it's all X is the Y, then X is inside, Y is going to be outside. So all firefighters know CPR. That means firefighters are inside. CPR, people who know CPR, outside. Okay, that's premise number one. Premise number two is Jill knows CPR. So Jill could be here, or Jill could be here, right? These are two possibilities for Jill. So I drew two possible premises. Conclusion is, therefore, Jill is a firefighter. Okay. But I noticed this is also a possibility. So in this case, Jill's outside of firefighter circle. That means Jill doesn't have to be a firefighter. So I found the case where Jill knows CPR, but Jill's not a firefighter, right? So invalid. Because Jill could be, because this is possible. That means this is my counterexample. This is a counterexample because if this is possible, then conclusion is false. Conclusion says Jill is firefighter, but this person is not a firefighter. But this person knows CPR, right? So this argument is invalid because of this particular counterexample. All right, I'm gonna do one more. I'm gonna have you finish the rest of the Euler diagram. All right, next one. It says some film students are nice and some nice students are fun. So those are my two premises. Okay, I noticed it's some something. So some x's are y. So film, they mean they have an overlap. They're not inside of the other, nor they're disjoint. So here I'm going to say film and nice. Okay, let's look at the second premise. Some nice students are fun. So what are possible ways I can draw this? Again, nice and fun, they're not one on the other side, one inside the other. They have an overlap, they're not separated. So it's possible that it'd be like this. This is one possibility. That means fun and nice they have overlap. It's also possible it's like this, right? So I have two cases for fun to be. Those are two possibilities. All right, let's look at the conclusion part then. Conclusion says some film students are fun. So I want to see if I can find the counterexample, because if I can find a counterexample, then the argument is invalid. It says some film students are fun. What's the negation of that? No film students are fun. So what if you are here? What if this was the case, right? Then fun and film, they don't have anything in common. That means no film students are fun, right? But this was possibility, right? So this is going to be invalid because this is possible. This is possible. And this is no film students are fun. So that's my counterexample. I can't come up with a case where no film students are fun. That still satisfies condition 1 and condition 2, but the conclusion is false. Conclusion says some film students are fun, but here I came up with the case where no film students are fun. All right, I'm gonna have you try the next 3 examples, and then we'll meet back after that. All right, now we're gonna evaluate the validity of an argument with the truth table. So it's kind of like what we did before. So now we can do the same thing. We can do truth table for the argument. So how does it work? We'll rewrite the argument using symbolic form. That's like what we did before. We're going to create a truth table as in the usual way. Fill out the truth value of each component. We're going to create the columns for all premises. We're going to create a column for conclusion. So we're doing kind of setup. We'll make columns for all premises and conclusion. And then basically the same concept. If you can find the case where all premises are true but the conclusion is false, then the argument is invalid. That will be my counterexample. If there isn't any case where all premises are true but the conclusion is false, then the argument is valid. So same logic, we're going to use the same logic, but we're just going to put it in terms of a truth table. All right, let's look at the next question. Number 8. If I finish all my homework, I play a video game. Wow. Yesterday I finished all my homework. Therefore, I played a video game. Okay, so there's homework, there's a video game. If there's first statement says if, then, that's the premise. Yesterday I finished all my homework, that's the premise. Therefore, I see the little 3 dot symbols, so that's the last statement is conclusion. So I have premise 1, if, then that's premise 1. Yesterday I finished my homework, that's premise 2, and then we have conclusion. Okay, so it's symbolic form. Let's translate the first statement into symbolic form. If I finish all my homework, then I play video games. So homework, then video game, right? So H is homework, V is a video game. It says if then statement, so V implies H implies V. Another premise is I finish all my homework, so H. And the conclusion is therefore I played a video game, this V. So my premises are V implies V, H implies V, H, my conclusion is V. Okay, so I'm going to kind of start the same way. H, and there's a V, true, true, false, false, true, false, true, false. So nothing fancy, I'm just following just normal way of starting truth table. Now I want to make columns to have all my premises. So the first premise is H implies V, so I'm going to do that. H implies V. Again, when is the only time H implies V is false? When your antecedent is true and your consequent is false. This part, right? That's when we have false. Everything else is true. This is from last section. So that's their statement. How about the second premise? So I'm going to write that. So it's just H. So I don't have, I'm just going to copy H here. You don't have to copy it, but I'll do it just so that visually it looks nice. So 1 is done, 2 is done, 3 is my conclusion. So they say just do the conclusion part 2. I'm like, okay, fine. Maybe do it in red. Conclusion is just V, so I'll just copy V. T, F, T, F. So that's 3. So premise column here, first one, premise column here, the second one, and then conclusion column here, right? So how do I know the argument is invalid or not valid or valid? In order to show that this is invalid, I have to show the case where all the premises are true and the conclusion is false. So I'm looking at all my rows. Is there a case where we have true, true, false? I don't think so. We have true, true, true. We don't have true, true, false. We have false, true, true, false. But so yeah, we can't find that. That means my argument is valid. Valid. No. True, true, therefore false. I'm gonna try one more and have you finish the rest of it. Okay, it's kind of similar. If I finish all my homework, I play a video game. Fine. Yesterday I played a video game. Conclusion, therefore I finish all my homework. So in symbolic form, same thing. If the first statement is if then statement, so homework and then video. So homework implies video. So that's premise 1. Premise 2 is yesterday I played video games, so V is premise 2. Conclusions, therefore there's 3 dots. So this is conclusion, right? I finished all my homework. So therefore I finished all my homework. H. Start the same way. True, true, false, false. True, false, true, false. Okay, so this premise 1, premise 2. That's my conclusion. So premise 1, I need H implies V. Kind of same thing. H implies V is false only when you have true. Antecedent is true, implies false. So the second column, that's false. Everything else is true. So that's 1. And then second premise is V. Just going to copy that. V is T, F, T, F. And then conclusion, I'm going to write it in red. Conclusion part is going to be H, so I'll just copy H, T, T, F, F. So I wrote my first premise column here. I wrote my second premise column here. And then I wrote my conclusion column here. So I want to see if I can find true, true, and false. So in order to find something is invalid, I need to find something where we have true, true, false. Well, first column, first row, I have two TTT, but then this one, ooh, I think I found it. So invalid, because we have true, true, therefore false, right? So if that's the case, then this is invalid. This is my counterexample. Let's look at the counterexample. What counterexample is? Here, this is a case where you did not finish homework, but you play a video game, right? If you kind of think about it in terms of common sense, which we're going to talk in more detail next worksheet. Like the premise says, if you finish all my homework, then I play a video game. It doesn't say anything about if you don't finish your homework. According to this, I could still play a video game, right? So just because I play a video game doesn't mean I finish on my homework, because it was possible that I didn't finish my homework, but still play a video game. It doesn't contradict the first premise, right? So this is why the argument is invalid. Okay, I'm gonna have you finish the rest of the worksheet, and I think that's 2 more, and then that's it.